Hello. In this video, I'm going to talk about Chapter 25, Electromagnetic Induction. And I would say this is the highlight of this course. So I'm happy that you guys are here. And finally, we got here and you want to see all things together that you learn. And then finally, you're putting things together, I feel like. And it goes into another level that I wanted to talk about, but I guess that we're running out of time for this semester, but we'll see how it goes. Okay, so electromagnetic induction. I made this just now. What's this? Is just a wire. This is just nothing special, regular wire, copper wire. I made copper loops, wire loops, 700 turns. I counted. And around the toilet paper roll. That's it. Nothing, no batteries, nothing. But the end of the two ends are connected with this LED diode. So there's a LED. Obviously, it's not connected to the power, no battery supply, so that's it. It's not doing anything special. However, I'm going to show you this video now, and you're going to see what's going to happen to it. Sorry. Okay, share screen. Which one is it? It's this one. Okay. Let's try this. Should be good. All right. Here. All right. So here you go. Okay. Here you go. Hello. So what do we have here? What's this white stuff? What's this white stuff?
Toilet paper roll.
Toilet paper roll. And I put copper wires around it. How many turns do you remember Mommy turned it diligently?
700.
700 turns.
700.
700. So yeah, and you see just around the toilet paper roll. There's nothing else. And then two ends are connected with LED. That's it. There's no power source. It's just a loops of wires and light. So what else I have here is the neodyme magnet. Yeah, so this is the magnet. It's just a very strong magnet. That's all. Very strong magnet. Then what I'm going to do, or I asked my assistant to do, is to drop this magnet into the inside the toilet paper roll. So I just drop the magnet. Because this is LED, we have to be careful with which side we're going to drop it, but I'll explain that later. But we just drop this magnet through and see what happens to the light. That's this one. Okay. All right, one more time.
Okay.
All right.
1, 2, 3, go.
Yeah, it lit.
Got it?
See? Okay. Do again, Focus please. on the light. I'm a little
Okay.
more
Get
the light. Focused.
All right, why don't you see the lights?
Yeah.
Here.
Here. Okay.
Good?
Yeah.
More?
Yeah. So you see the light got lit. When we drop this magnet, light gets lit. There is no battery connected to it, but suddenly there is a current. And this is the electromagnetic induction. I put this magnet on the screwdriver end, and this screwdriver, because it gets attached, it can be attached to it. So I can put the magnet in and out, in and out, in and out, in and out very quickly. Let's see that. This one. Okay, now you see in and out. Change in magnetic field induces current in a wire. Induce current, induce voltage. So it's not connected to the battery. It's just a change in magnetic field. And the one we have, the magnet again, is the neodymium magnet. Right? All right, say bye.
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 Bye. All right. You see, if you have a magnet approaching, then the inside the coil, I'll come back here. So this is the coil right here. And I have a, oops, I put it really close to my phone. The magnet approaching. Let me see if I can do it. Maybe it's too hard from this angle. If it approaches like this, maybe not, over here. Yeah, you see it? It sometimes lets it, because this is diode, so the direction matters. But what's happening is that by a magnet is passing through, it won't do anything if I just leave it inside. If I just leave it inside, stationary magnet won't do anything. Only it lets only when you have a magnet in motion, means that change in magnetic field. Remember, electric charge that's not moving don't have any force applied, no magnetic force. Electric charge can be in the external magnetic field, and if it's not moving, there's no force applied. If it's in electric field, of course, it's going to feel the force, electric force, but it's going to moving electric charge in an external magnetic field feels the magnetic force on the moving electric charge. So this one now, what's happening is that you have a magnet passing through. That means this magnet generating a magnetic field, and this coil, closed loop, feels the change in magnetic field, so it induces current, moving charges to try to resist the change in magnetic field. So let's see, if I have a magnet north and south that's pointing, I don't like putting it close to my phone. If the magnet that's pointing, maybe I can do this with my, pointing in this direction, let's say, north and south, right? So it's creating a magnetic field, something like this. And then if it's passing through, then this loop feels that, oh, suddenly it's magnetic field passing through in this direction is getting strong. And this closed loop feels the change in magnetic field, and they don't like it. So they induce the current to oppose the change, so the current will run in this direction using the right-hand rule, right? This is the direction of the magnet, is my thumb now. And then so this magnet is coming this way, so this coil don't like it. So it wants to induce the current in my right hand fingers to oppose the change in magnetic field. So it turns in this direction. So there will be induced current and induced voltage to try to resist the change in magnetic field. So once there's not so much change, there's no voltage, no current, nothing. But only it happens when there is a change in magnetic field. So I could just put the magnet here, and when it just comes nearby, it's gonna light up. But then if I'm stationary putting it there, it doesn't do anything. And this induced voltage or induced current, it depends on by number of loops. The more number of loops of the coil you have, the wire you have, then you have more current. It gets stronger because remember, more turns you got, then you can create more magnetic field. So that depends on the number of turns. Of course, it depends on the resistance. The voltage will be depends on the resistance. And also depends on the speed of the magnetic field, changing magnetic field, the rate of a change in magnetic field, right? If the magnetic field is not moving so much, if it's not changing so fast, then it's not going to induce much voltage or much current in a coil. So let's see. So that's it. You see, there's an induction. I'm going to show you this slide here. Here. So this is the electromagnetic induction discovered by Faraday and Henry. The voltage is induced in closed loop that doesn't have any battery here. No battery, but you can light up or you can even charge your phone or do stuff with it when you have a change in magnetic field. So that's called electromagnetic induction. There is voltage induced, and that amount of voltage, induced voltage, can be increased if you have more number of loops on the wire. So I made 700 turns. Initially, I tried it with 100 turns. It didn't lit. So I increased to 700, and I wanted to do 1,000, but I'm like, oh, let's try with the 700 turns, and it worked. So I was counting, literally counting up to 700 for you. But anyhow, so increasing the number of loops, increase the induced voltage, and increasing the speed of a magnet, or the increasing in speed of change in magnetic field. Also changes or increase the induced voltage. So the slow motion is not too much voltage. If you're moving so slow, even though the magnet is very strong. So it has a strong magnetic field, but if you're moving slow, then not too much voltage. But if you move fast, then yes. So you can try to see this by just put the U-shaped magnet on the closed wire and see if you can just remove the closed shape, just a loop in the U-shape, in between the U-shaped magnets. If you can get it out, it's going to be very hard because you're trying to change the magnetic field that's passing through this closed loop, and then it's not connected to the battery. It's just a coil of a wire. But you have a magnetic field that's passing through, and if you want to move it, right, take it off, then that means that it's going to change the magnetic field. It's going to induce the current to try to resist the change. So it wants to stay where it's at. It wants to stay where it's at, so you feel a very strong resist. And you're going to see the ammeter or voltmeter is going to be deflected because there's going to be a current all of a sudden that's going to be running. So again, when a magnet is plunged into a coil, just a coil, again, no battery, and if you have twice as many loops, then you're going to have twice as much voltage induced. So more number of loops means more voltage induction induced. So Faraday's law, this is called the Faraday's law, that states that induced voltage in coil is proportional to the number of loops. Also depends on the rate at which magnetic field is changing inside the loop. So you want to have a strong magnet, then you want to have a bigger, strong magnetic field, then that big, strong magnetic field moving, changing fast is going to give a big effect. If you have a weak magnet, so the magnetic field is not strong, then you really have to move it fast to get that bigger, to see the effect of an induced voltage or induced current. And also the Faraday's law says that amount of current, you have an induced voltage, therefore you're going to have a induced current, and that's by the electromagnetic induction. Is of course depends on the resistance of the coil, what kind of a circuit it's connected to, what kind of electronic device, like the one that I have is the LED light, you know, so the current depends on that, and then also how the voltage is induced. Makes sense, right? So if you have a magnet that you want to put it into a coil that has many loops, you're going to feel the resist the motion of magnet. Okay. Let me share something. I'm going to stop the video for a moment. So let me share this screen here. Okay. Here.
That's awesome.
Before you put that away, Glenn,
Hold on, am I running? Okay, we're going. Yeah.
your phone is better than mine.
Wow. Do that again.
Yeah, it's
That is.
So you see it. You see what's happening is that this magnet is just passing through this copper pipe. It's just a pipe, but when it's passing through it, there's going to be an induced current on the pipe inside the copper pipe. You know, then this current, it generates it's induced to resist the change in a magnetic field. So the magnetic field is trying to increase in this direction. So the copper pipe induces the current in this direction to change. So there's a resistance, repel force, the induced magnetic field, and then dropping coil. Want to see again?
That's awesome.
Before you put that away, Glenn,
Hold on, am I running? Okay, we're going. Yeah.
your phone is better than mine.
Wow. Do that again.
Yeah, it's
That is. That's awesome.
Okay. All right. Yeah. So that's that. So you see that the induced current, it don't like the change, and it even resists that motion. Let me see. Also, I want you to see. I'm going to let me stop it again. Okay. So let's see. I have an image that I want to share. So the tap card or the credit card or that kind of a thing, the plastic card that you just, when you ride on a metro, you tap it. And then somehow it registers, and then they know how much money you have in a balance, and then they know how to charge it when you rode on that transportation device and all that kind of stuff. They know it. So that means that it has a microchip inside. But do you think the plastic card has enough space to have a battery? If it has a microchip that you have to have it changed to be read by the computer, how does the power, where does the power come from? So here is a picture image. So this is an X-ray image of tap card or the credit card, I'm sorry. So you have a microchip here, and then you see there is a wire, thin wire inside the card. What's that wire is doing? It's the closed loop. It's the closed loop. So what happens when you bring this plastic card? Tap it or do this. This, when you're tapping into, has a magnet, or it could be an electromagnetic coil, right? Then you have a magnetic field. You bring this card that has this closed loop, bring it, increase in magnetic field. So at that moment, you have a induced current. You don't need to have a battery. Sometimes you might have seen those devices that have, you can just like tap it, put it on, and then you can charge your iPhone now. How does that work? Because iPhone, inside iPhone, you can just have a loop, and then if on a device that you could have a magnetic field that's constantly changing. So electromagnetic coils that's like flipping, it's in AC, so it's alternating, so it's changing the direction constantly. Ooh. Then you constantly have changing magnetic field, and then if you have a loop in the phone wire, then it induces voltage. You don't need to have a wire connected to your phone to charge it anymore. I have this. Oh, I keep talking, looking at this. Stop sharing. So like this is I used to get into the classroom in a college that we don't go anymore, but I tap it, right? So inside here, if I see the X-ray, pretty sure there is a wire like this. And then I just tap it. So there is a, at that moment, there's a change in magnetic field that's passing through, induces the current. It doesn't need to have a power. It doesn't need to have a voltage, battery inside. How does the traffic light get triggered? When you approach to the traffic intersection, sometimes in asphalt, pay attention, even on the freeway, they have it. You see a big wire in a road. So you come, your car comes, and then there's a big wire loop like this, like loop like this on the road, and then a car comes. This is connected to the traffic light, but why? So I want you to be able to explain that. We're going to discuss in a discussion. Again, make sure that you go over the Faraday's law, that the slide that I made you, and then here I can show you this slide to share. Share screen. Here, electromagnetic induction. So applying the Faraday's law, you can activate the traffic signal. All right, so the car is approaching and stops. And security system. Why is you can trigger the security system? Scanning magnetic strips on the back of the credit card, sound tape, electronic device in the computer hard drives, and iPads. Sorry, this is old. Yeah, how does the security system work? So you go into the airport and then you pass through, there's like a big white stuff that you have to pass through, right? They say, make sure to take off keys and no belt that has a metal. So you gotta make sure to take off those keys and metals out from you. Why? What's different from metals and non-metals? Metals are conductors. Conductors have, what does conductor have and then insulator don't have? Conductor have free electrons. Those free electrons, right? So when you're holding a metal, right, metals, and then when this metal have free electrons, what's the moving electrons? I move this key. I move with a metal. What does moving electrons mean? What's the name for the moving electron? Electric current. When you have electric current, what does electric current do? The electric charge generates electric field. Moving electric charge generates magnetic field. Also electric field too, but magnetic field. They're going to both induce, there's going to be a magnetic field also generated, produced by the moving charge. So when I move this key like this, it has free electrons. This is like a current, and therefore I'm generating a magnetic field, both electric field and a magnetic field, like just doing this. So then I move with the key, or if I have a gun in my pocket that has a metal, right? And then the gun has the free electrons, and I'm moving with the gun that has the free electrons. It becomes a current. I'm generating magnetic field, and I'm passing through this big coil that can detect a change in magnetic field. So the coil, the machine will beep because there's going to be an induced voltage in the machine. If you don't have a metal, there's no induced voltage. So that's how things work. Then you might want to think about how the traffic signal works, right? So I want you to try and explain it with the similar analogy that I just made with triggering a security system. All right, so this is one of the highlights for the class, and then we're going to also talk about field induction, or I want you to read about it. It's nothing much. Just going to show you that 1 or 2 slides, but that's it. Okay, so I hope you enjoyed it. I'll see you in the discussion.